Hello, chemistry students. Welcome to the second and final installment of your Chapter 7, Section 1 notes, starting with the number of particles in a mole. We're going to start by talking about the number of particles in a mole. We need to remember that matter is made of atoms, molecules, and ions, all of which are much smaller than apples. If you remember, we kind of ended our last section of notes with an example where we figured out how many seeds there were in 14 kilograms of apples. Okay, and that's something that potentially you could count. However, okay, when we're talking about atoms, molecules, and ions, which are tiny and we can't see them even with a microscope, okay, it's not really practical to count them. So counting particles one by one is not practical. So instead, chemists use the mole. The mole of a substance is 6.022 times 10 to the 23rd representative particles of that substance and a mole is the SI unit of measuring the amount of substance. So remember SI, that refers to that Le Système International de Unité, so that international system of units that's used all around the world. Okay, so scientists all around the world use a mole to measure the amount of substance. Specifically, a mole is going to be 6.022 times 10 to the 23rd representative particles of that substance. So that number has a special name. It's called Avogadro's number. And Avogadro's number is the number of representative particles in a mole, which is 6.022 times 10 to the 23rd. So, again, on the ChemQuest that you did about intro to moles, you did some calculations where you found out that with phosphorus and I think it was carbon, and you figured out how many atoms there were in this number of grams, and again, it turned out to be this magic number here. Avogadro's number is that special number showing the number or representing the number of particles in a mole. So what do we mean by representative particle? Representative particle refers to the species present in a substance. We've talked about representative particles before. We've kind of said it's the smallest piece that still has all the properties of the substance. And so far we've talked about 3 different kinds of substances. So if you would just rack your brain for a moment here and think about what are the substances that we've talked about. Well, one of the substances we've talked about is an element. Another one of the substances that we have talked about is a molecular compound. And remember, we know something's a molecular compound because it's made of 2 nonmetals. And our last kind of substance is an ionic compound. And remember, we know it's an ionic compound because it's made of a metal and a nonmetal. Or it has a polyatomic ion in it. So those are our 3 types of substances that we've talked about. So again, we've talked about this representative particle idea before. Again, we're talking about if we have a big chunk of element, what's that smallest piece I can chop that element up into and it still has all the properties of that original element? Well, that smallest piece of an element is an atom. For a molecular compound, again, if I have a big chunk of molecular compound and I want to chop it up into small pieces, but I want those small pieces to still have all the properties of that original big chunk of molecular compound, that smallest piece is a molecule. I'm going to abbreviate molecule MOLC. It has to have the C on there because an MOL is a mole. And lastly, an ionic compound. Again, the same idea. Big chunk of ionic compound, what's that smallest piece I can chop it up into and it still has all the original properties of that ionic compound? That smallest piece is called a formula unit. And remember, everybody likes our abbreviation for formula unit because it's FU. Okay, so again, back here, we look at that definition again, okay? Mole of a substance is 6.022 times 10 to the 23rd representative particles of that substance. If that substance is an element, that representative particle is an atom. If that substance is a molecular compound, that representative particle is a molecule. And if that substance is an ionic compound, our representative particle is a formula unit. So, the mole is important because, sorry about that. The mole allows chemists to count the number of representative particles in a substance. And again, it wouldn't be practical for a chemist to try to count starting at 1 to 6.022 times 10 to the 23rd. Okay, so again, this is a practical way for chemists to talk about how many representative particles we have in a substance. Again, if I'm talking about an element, my representative particle is an atom. If I'm talking about a molecular compound, my representative particle is a molecule. If I'm talking about an ionic compound, my representative particle is a formula unit. Now, don't forget about the diatomic molecules. Remember, this is Brinkelhoff, okay, so there were 7 of them. Okay, so hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. These technically are elements, but they always exist as diatomic molecules. So the representative particle for these 7 substances is a molecule. So even though these are technically elements, because these elements never exist as a single atom in nature, they're always bonded to another atom of their same type, making them a molecule. Their smallest piece is always a molecule. So this chapter is about math, so we want to talk about our math, our conversion factor. Remember, our conversion factor is like a ratio of equivalent measurements. Equivalent means they're equal. So here's a generic one for this, and then we'll kind of look at some specific ones. So we can say that 1 mole of substance over 6.022 times 10 to the 23rd representative particles. Now, the power of a conversion factor is that depending upon where I need my units to be, I can flip them. So it's just as correct to write this as 6.022 times 10 to the 23rd representative particles over 1 mole of substance. Typically, you don't write both, but I just want to show you that depending upon where I need the unit mole to be, if it needs to be in the numerator or denominator to cancel out when I start to do problems, I can put it wherever I need it to be by flipping this. So this is generic. Most of my chemistry students don't really remember the generic one. They remember the specific ones. And by specific, I mean going back to this chart here, right? Specific for these 3 different kinds of substances. Okay? I'm not going to write these both ways. I'm just going to write them one way or the other. Okay? So, if I have 1 mole of element, then I have 6.022 times 10 to the 23rd atoms, because our representative particle of an element is an atom. And again, I could flip this. Okay, I could put 6.022 times 10 to the 23rd atoms over 1 mole of element. So that's our specific conversion factor related to an element. For a molecular compound, I can say I have 6.022 times 10 to the 23rd molecules in 1 mole of molecular compound. Again, same thing as what I have up here. I've just taken substance and made it molecular compound and representative particle, because the representative particle of a molecular compound is a molecule. I put molecule in here. Okay, so again, this is just the specific one for molecular compounds. So there's one more. Hopefully you can kind of figure out what that might be, right? That's going to be 1 mole of ionic compound over 6.022 times 10 to the 23rd formula units. So let's see how we use these to solve a problem. So our problem is, magnesium is a light metal used in the manufacture of aircraft, automobile wheels, and tools. How many moles of magnesium is 1.25 times 10 to the 23rd atoms of magnesium? Now, Many times these are going to be story problems. And oftentimes, students don't particularly like story problems. So I would encourage you to always sort of take the question and sort of make it a little bit maybe simpler. So what I'm going to do is I'm going to say the problem is really asking me to take 1.25 times 10 to the 23rd atoms of magnesium and figure out how many moles of magnesium that is. That way, as I solve this problem, I don't have to look back at those couple sentences that the problem has given me. I can just look back at this statement, because this problem's asking me to take atoms of magnesium and convert it to moles of magnesium. Now, what I would encourage you to do if you have an index card at home is start what I call the chemistry toolkit. Could even just do it on a little small piece of paper, okay? You're going to get a total of 5 tools. And sometimes when you're new at doing these problems, it's helpful if you have your tools to look at. So what you can put on your kind of toolkit right now are these 3 conversion factors. Okay, and we'll add a couple more as we move through this chapter. So the idea is with this chemistry toolkit is kind of the same idea that if you were building something and you had never built anything before, right? If you looked at if you had a hammer, a Phillips screwdriver, a Phillips head screw, and a nail. Okay, my guess is that by kind of looking at the Phillips screw, that you could figure out that the tool you needed to use was the Phillips head screwdriver. So it's that same kind of idea with your chemistry toolkit. When you're kind of struggling or when you're new at doing these problems, sometimes it's helpful to be looking at what your choices of tools are to decide what tool to use. So when I look at this problem, I notice that my units again are atoms and moles. So I'm looking for a tool here that has atoms and moles. So that tells me what tool I'm going to use. So I'm going to use this one here when I do this problem. So I always start these problems with my given, which is the 1.25 times 10 to the 23rd atoms of magnesium. So to cross out atoms of magnesium, you can always kind of think of them as being over 1, right? I don't ever write them when I do them in notes over 1, but you could write these as being over 1. Okay, which means atoms is in the numerator, so I need atoms of magnesium to be in the denominator. I look back again at my tool, and the other units for that are going to be the moles of the same element. So I'm going to have moles of magnesium as my other unit. Now, I'm curious about the numbers. I just look here, right? The number in front of moles is 1. The number in front of atoms is Avogadro's number. So that means I need the number in front of moles to be 1 and the number in front of atoms to be 6.022 times 10 to the 23rd. Again, I want to take the time to look and see that my units are crossing out. I have atoms of magnesium in the numerator. I have atoms of magnesium in the denominator, which means I'm left with moles of magnesium, which is what I want. So again, this is a good one to check on your calculator and see that you're able to get the correct answer. You should get 0.208 moles. And again, because of significant figures, which we talked about briefly, and you have a handout that you got about significant figures and the rules, when I'm multiplying and dividing, I'm limited by the fewest number. This has 3 sig figs, and this is a definition, so this has unlimited significant figures. So my answer can only have 3 sig figs. So I have to write my answer as decimal 208. Remember, this is not a significant digit, and this 0 is because it's between numbers that are not 0. As a quick aside about how you put this in your calculator, for those of you that are still struggling with your calculators, right? 1.25, you're going to use that E button, 2, 3. I know I'm dividing because my Avogadro's number is in the denominator. So divided by 6.022 E23. When you type that in your calculator, you should get 0.208 moles of magnesium. Again, if you need a moment to do that on your calculator, go ahead and pause the YouTube. Okay, I'm going to continue going. So the next part of our notes is about figuring the number of atoms or ions in a mole of compound. And to do this, you must know how many atoms are in a representative particle of the compound. That is determined by the chemical formula, which is why it's still important that you remember how to write the chemical formulas for ionic and molecular compounds. Remember, when you're given the name of a molecular compound and asked to write the formula, the prefixes become subscripts. Remember, when you're given the name of an ionic compound and asked to write the formula, you're going to write symbols, charges, crisscross, lowest whole number ratio. So, to look at an example of this, if we're talking about carbon dioxide, right, that's a molecular compound because it's 2 nonmetals, and my prefixes become subscripts. There is no prefix on carbon, which means there's only one, so my formula would be CO2. Now, we know that in 1 molecule of CO2, there are 1 carbon atom plus 2 oxygen atoms, giving me 3 atoms in total. Okay, hopefully everybody's okay with that. So, what that means is, in 1 mole of carbon dioxide, I'm going to have my Avogadro's number, molecules of carbon dioxide. So by definition, okay, if I have a mole, I have to have the representative particle. And in this case, because this is a molecular compound, my representative particle is a molecule. If I want to get to atoms, then I have to know that 1 molecule of CO2 has 3 atoms. So, again, let's take a look at a problem that involves this. Our problem is propane is a gas used for cooking and heating. How many atoms are in 2.12 moles of propane, C3H8? Again, usually these are going to be story problems in chemistry, so again, I like to kind of summarize what I have. So this problem is asking me to take 2.12 moles of C3H8 and figure out how many atoms that is. Okay, again, I look at my chemistry toolkit, right? So I go back here and I'm looking for something with moles and atoms. I come back here, I start to look, and I see atoms and I see moles. But notice the substance is an element. Is propane an element? No. Propane is not an element. Propane is a molecular compound. So I can only convert moles to molecules. So if I start with my given 2.12 moles of propane, I know moles will have to go on the bottom to cross out. And based on that tool, I have to have molecules of propane on the top because propane is a molecular compound. So this is going to be molecules of propane. Now, again, numbers, I don't care if you do them now or at the end, so we'll do them at the now, right? The number in front of molecules is Avogadro's, and in front of moles is 1. So in front of moles is 1, and in front of molecules is 6.022 times 10 to the 23rd. If I kind of look at my units right now, my moles are canceling out, but I'm left in molecules, and I don't want molecules, I want atoms. So I know that molecules of propane are going to go on the bottom, and somehow I have to convert them to atoms. Well, that's where we're going to use what we just talked about with carbon dioxide, right? When we have 1 molecule of CO2, we know that there's 3 atoms because there's 2 oxygens and 1 carbon. Well, if I have 1 molecule of C3H8, I have 3 carbons plus 8 hydrogens, which is a total of 11 atoms. Molecules and molecules cross out, so I'm left with my answer in the correct units that I want, which is atoms. And again, this is one that I definitely would like you to try on your calculator. You should end up with 1.40 times 10 to the 25th atoms. Again, I need to have 3 significant figures because this has 3 sig figs. This is that definition, it is unlimited. And this also is a definition and is unlimited. Okay, so my answer has to have 3 sig figs. Again, in case you're struggling, how do you put this in your calculator? 2.12 times 6.022 23 times 11 should give you your answer. I know I'm multiplying every time here because my numbers are all in the numerator. I'm only going to divide my numbers when they're in the denominator. So, hopefully these 2 problems help you out. Do know that I will be making a video key corrections for homework number 10 for you. So if you struggle with the homework, give it your best shot. Set up the problems. Show all of your work, okay, for all of the problems. But I will be making a key with corrections, kind of talking through and explaining how to do those problems. Have a good day. Talk to you later.